Has it been recorded?
It's recording now. Yeah, it's recording now.
Okay, good. Do I need to get someone else, or are you good?
I think I'm fine.
Okay. So what this is saying is, if there's some special point which represents the function on that interval, but here all the representative points there are to choose from are in fact increasing at a rate of 0, that means every interval must increase at a rate of 0. Okay, let's write this out. How can we actually show that something is a constant function? It's a little bit tricky logically to think about how to do that. Well, okay, first let's like start the theorem. So this theorem is a conditional. It says assume the derivative is 0, and then we're going to show that it's constant. So let's do it. Assume that the derivative is 0, and now my goal is show f is constant. How am I going to show that f is constant? Well, I'm going to show that f is constant by picking any 2 points whatsoever on that interval and showing that they are the same. So here's like my picture. Here's A, here's B, and now I need to show, well, I don't even know that, so I'll erase that. Yet. How can I show that this function has the same value everywhere? Well, to show that it has the same value everywhere is the same thing as saying that for any 2 values that they are the same. So let's pick 2 arbitrary values, call them x1 and x2, somewhere here on this interval between A and B. And my goal is going to be to show that f of x1 has to equal f of x2. Why does f of x1 have to equal f of x2? Russell?
That's the only way to make the derivative 0.
It's the only way to make the derivative 0. Yeah, let's be a little bit more careful about that. Basically what we're going to do is we're going to apply the mean value theorem to f on the interval x1, x2. If we apply the mean value theorem to f on the interval x1, x2, what does it say? It says there exists a c on the interval x1, x2, such that f prime of c is f of x2 minus f of x1 over x2 minus x1. But then you look at that for a second and you realize, oh, this, by my assumption, the derivative is 0 everywhere. So if this is 0, then this fraction has to be 0, and the only way for that to happen is if the numerator is 0. Was that too fast, or are we good?
Yeah. Okay.
That proves that the y value is the same for these 2 numbers. And then if you think about the significance of that, I've just taken 2 arbitrary points and have shown that they have the same y value. But then Noah Fang, I can take 2 different points, right? I can now say, all right, well, I did it with x1 and x2. Now let's do it with x1 and x3. Well, by the same logic, x1 and x3 must have the same y value, right? And then I can repeat it again. Now I'll take x2 and x4, right? By the same logic again, x2 and x4 must have the same y value. And so if I can take any 2 values whatsoever on that interval and I always get the same y value, then in fact all of the points on that interval must have the same y value, and I've shown that that function is constant. Cool? I think that's cool. Maybe it's not that cool because it's kind of a little bit of a boring theorem. But anyway, there it is, mean value theorem. Alright, this can be used, there's kind of a corollary to this. A corollary is kind of like another little theorem that you get as a consequence of a more important theorem. But this one's actually pretty important, and it goes back to something that we talked about like a month ago. What can I say, or maybe not quite that much. What can I say about if 2 functions have the same derivative? So if f prime of x equals g prime of x, then what can I say?
They are parallel.
About those 2 functions. Think about it for 10 seconds. I mean, I know we kind of did this already, but. Richard, what could I say? If the two functions have the same derivative, what do I know about them?
They have to have a derivative of 0, or they have to be odd.
Okay. No, I don't think so. John Park again.
It's like a shift of the other one where it's the same like graph thingy.
Yeah, it's like the shift of the other one where it's the same graph thingy. Yeah. They are, in fact, vertical translations of each other. We talked about this, Rich, remember how we talked about this a couple weeks ago? Like, I think I did that in this class. We talked about how, like, the derivative is like the coach, which is like blowing the whistle and telling everybody to do the exact same thing the exact same time. Did I talk about this in this class?
No.
I don't think so.
No.
I think so. The derivative of a function is the rate of change of the function. So, if two functions have the same derivative, then they must both be increasing at the exact same rate. So if two functions are both increasing at the exact same rate at the exact same time, then it's like the two functions are essentially following the same directions. So if you think of the derivative as like these are like synchronized swimmers or something like that, right? And the derivative is like saying, go up, no, now stop, now go back, now go down, now go up. I swear I talked about this.
We
Maybe
did.
I did. Okay.
Okay.
All right. Anyway, but anyway, John Park, you figured it out on your own. Yes. This is a theorem. Also doesn't have a name. It's actually a very important theorem. If two, note, again, we'll go over here to the we already did this wall. Again, it is trivial. That if two functions differ by a constant, it is trivial to prove that they have the same derivative, because you just simply differentiate both sides, right? And the derivative of a constant is just 0. Done. So this is the converse of that. This says that if two functions have the same derivative, then they must be differ by a constant. Okay. How do we prove this?
Using the mean value theorem.
Good spirit. However, no. It is a corollary, which means it's basically just the theorem we just proved, just adding like one line or something. Oh.
Is it something you like
Oh,
subtract?
wait, you subtract the 2.
Yup.
Yeah.
And go on. Explain. What do we do?
You sort of like subtract between the 2 and then derive, and then you know that, like, yeah.
Yeah, okay. So let's suppose that two functions have the same derivative. Now prove to me that they must differ by a constant. I'm going to force you to say this properly.
Okay. Yeah, so then you sort of you can like subtract g of x or the derivative of from both sides, and then you're like it's 0.
Okay, that's fine. Yeah, that's pretty fine. It's I think it's a little bit cleaner if you just make a new function.
Yeah.
So make a new function. So let h. But yeah, what do you say is fine too? Let h be a new function which is just f of x minus g of x. Okay. Now differentiate. What is the derivative over here is f prime of x minus g prime of x. But now, by assumption, these two functions have the same derivative. Thus,
It's 0.
0.
and what do I know about a function whose derivative is 0?
It's a constant.
So by previous theorem, h is a constant function. So h must just be like a constant. And there we have it. So f of x minus g of x, which is just h, is a constant. And so f is g of x plus c. Okay. Very, very important thing that comes up like in about like a month, or maybe less. If two functions have the same derivative, they must differ by a constant. Okay. More things. This today is all about proving all the things you can prove. What?
Oh no, you're going to the other board again.
Russell, if you don't feel like doing this, I can pass the job on to someone else.
It's fine, I'll do
Pass
it.
the torch.
You want it?
No.
You're only like 15, you can't be like sick of the world yet.
If I'm the one holding the camera, then I can't film myself, so,
Yeah, John Park has to star in the video, you can't be the cameraman.
yeah.
Alright. Yeah. More things. How next? More things. There's something, Josephine, there's something that we've been assuming for a while now. Or we haven't exactly been assuming, but we've been talking about it, we've been talking around it, we've kind of been working it into things that we thought of as being sort of obvious. And here, I'll just draw a picture. Has some kind of function, it's doing a little bit of this. And now I can like draw some tangent lines or whatever, like here's a tangent line, here's one, here's one, here's one, here's one, here's one, here's one. Okay, what's going on here? Aaron, what's going on with this function? What's the obvious thing? Note that the theme of today is using information about the derivative to conclude information about the function. What am I hinting at in this picture? Maybe it's not that obvious. What am I hinting at in this picture? Connie. What's going on with this function? Here are some derivatives. Here are the derivatives, like a big positive, now it's like a smaller positive, now it's 0, now it's like negative, now it's like a small negative, now it's 0, now it's positive, now it's a big positive.
I am reading it.
Oh no, I'm tired of calling on Andy Guan. Wait, rest of the class.
Michelle says it's changing.
Yeah, Michelle, what's going on? It's changing? Yeah, it's changing. But how? What information can I conclude about the Andy Guan?
It's curvy.
What?
That's what I was gonna say, actually.
No, wait, seriously?
Like when like the derivative.
Oh, I haven't asked like a real question yet. I guess what, I don't know. What's going on here? Look, here the derivative is positive, now the derivative is 0, now the derivative is negative, now the derivative is 0 again, now the derivative is positive.
It changes.
Connie again. Never mind. Oh, okay. Maybe we're not on the same page here. Okay, so look, here the derivative is positive. What's happening to this function while the derivative is positive?
It's rising.
It's getting bigger, it's increasing. Now the derivative is 0.
Stop changing.
Now the derivative is negative. What's happening to the function?
It's decreasing.
It's decreasing. Now the derivative is 0. Now the derivative is positive again. It appears the derivative is increasing. So yeah, there is a very deep connection, and the very deep connection, which we have been sort of talking about it, but not really using it formally, is that, yeah, when the derivative is positive, the function is increasing. And when the derivative is negative, the function is decreasing. I was waiting for someone to say that. No one said that.
I know that was like too obvious.
What? Oh, so you think it's like so obvious that you just like, it's like you didn't even think that could possibly be talking about that.
Like all this time.
No, we haven't been using it. We've been kind of talking around that issue.
I don't think we've talked around.
No, we have been definitely. Yeah, we used it when we sketched derivatives. That's right. But we never formally concluded that this is actually true, because in fact, what must this theorem depend on? Apparently the mean value theorem says no dismissively. Yes, you are right. In fact, before we can even talk about this, we need to first get ourselves a pre-calculus recollection of what it even means for a function to be increasing. So let's do that. So f is increasing on some interval a b. If and only if what? This is just straight pre-calc. They do this kind of crap in like algebra 2. So here's some function, here's a, here's b. My function is increasing. What does that mean, that my function is increasing on that interval? Who hasn't talked today? Alex, what does it mean if a function is increasing?
Each successive point is
larger than one previously.
Each successive point is larger than the one previously. Yeah, it's basically like that, except there's like real numbers, so there's no such thing as like the next real number. So you have to phrase it a little bit differently. Someone take what he said and like fix it up. What does it mean to say that this function is increasing? He says essentially each successive number is bigger than the previous one. Brassel.
F of B is greater than F of A.
Oh, f of b is greater than f of a. No, not good enough. Bad definition. Because, crucially, do we consider that function to be increasing on that interval?
Oh yeah.
No, we do not. No, not really. No. Anyone, take a stand. The answer is no. This function is not increasing on this interval. What Alex said was in fact correct, that each point must be bigger than the next one, right? So it has to be, when I say a function is increasing on an interval, I mean it's always getting bigger. And you go on.
Say two arbitrary points.
Oh, yes!
Two arbitrary points are like, yeah.
Yes. And Iglan says take two arbitrary points on that interval. For any two arbitrary points whatsoever, if you move right, then you go up. Move right, go up. That's like the four-word definition of increasing. If you move right, you go up. So formally, what we say is that for all x1 on the interval AB, and for all x2 on the interval AB, if x1 is less than x2, then what?
F of X2 is greater.
Banging going on next door. You're ruining my video.
F of x1 is.
Then f of x1 is less than f of x2. Yeah. Cool. Cool. Okay, so that's important background information to have. Notice that this definition involves no calculus. Now, this is a purely pre-calculus or kind of algebra 2 type definition. So now I'm going to, hey.
Mr. Rose, my friend, how are you?
Hey, pretty good.
I have seen Miriam before. It's not
Yes,
Mr. Rose.
that's fine, yep. Okay, so now we are going to prove this connection which you all thought was so obvious that we had already proved it, but no, we never did. So here's the theorem, also doesn't have a name. The theorem is, we'll do the decreasing case. If the derivative of a function is negative on some interval AB, then f is decreasing on the interval AB. We're going to prove this theorem. If a function is negative, then if the derivative of a function is negative, then it must be decreasing. Okay, and this is another one of these kind of trivial proofs, right, where there's not that much, it's not that difficult, the math is not difficult, only the logic is difficult. And just you have to just be very careful with your definitions. You just kind of like write everything down, and then it just happens. And the proof ends up being just like one line or whatever. All right, so let's jump in. The format of this theorem is a conditional. So how do you prove a conditional? Assume the antecedents, derive the consequent. So let's assume that we have some function f whose derivative is negative on the interval AB. All right, and then we're going to prove something. What are we going to prove?
Is decreasing.
Yeah, so prove f is decreasing on the interval AB. Okay. Well, now I have to go back to my definition of what decreasing even means. What does it mean for a function to be decreasing on an interval? This is what I mean by like definition unpacking. Camille.
That its slope is negative.
No, remember, that's why we took 5 minutes to for me to refresh your memory that whether a function is increasing or decreasing has nothing to do with calculus.
That each value is less than the previous one.
Yes, can you state that a little bit more formally? It's pretty much exactly what's on the board, but you just have to like change like one thing.
If x1 is less than x2, then
For all x1,
for all
x1 on the interval AB, and for all x2 on the interval AB, what should be true?
F of x1 is greater than x2.
Someone fix it up. Yanni, fix it up. Yeah, I need the full conditional. If x1 is less than x2, then, right, the definition of decreasing is essentially move right, go down, right? Move over, go down. So what I need to prove is that for any 2 points whatsoever on this interval, if I move right, then I go down. So f of x1 is greater than f of x2. Okay, so yeah, Camille, it's important to keep in mind like what actually, if you don't know the definitions of these things, then yeah, of course, then you kind of make the whole theorem sort of like meaningless if you just sort of. Okay, but so this is what we have to prove. Okay, how should we prove this statement? Maybe now's a good time for like a picture. Here's kind of like my picture. Here's A, here's B, here's x1, here's x2. And yeah. I have to somehow like prove something now. What do I do? Okay, we just basically start, right? If I have to prove that for any 2 points whatsoever, this conditional holds, then let's just take 2 points. So, take an arbitrary x1 on the interval AB, and an x2 on the interval AB, and what do I need to show? That, right? I need to show that if x1 is less than x2, then f of x1 is greater than f of x2. Okay, John Park, how do I prove this conditional?
You prove it.
Oh man. No, what do I do? Yeah, Yanni says just keep on going, man. I know how to prove a conditional by now. You just assume the antecedent, derive the consequent.
That's what I said.
Yeah. So assume x1 is less than x2, and then what we do is we show that f of x1 is greater than f of x2. Okay, so it seems like we haven't really done anything yet, and it's true, we really haven't. All we have done is just use the definitions of all these terms to just focus in on one particular thing that we need to prove. If I can prove this little boy right here, that f of x1 is bigger than f of x2, then I'm done. And what am I allowed to use to prove that? What are all the things that I've assumed? I've assumed that my derivative is negative, and I've assumed that x1 is less than x2. Okay. All I have to do is prove the thing in the red box. What should I do? Aaron, what's the theme of today? What's the theme of today? The mean value theorem. So, what should we do?
You just you just say that like a negative derivative is equal to f of x minus.
Yeah, let's just do it, right? So we just do it. So apply the mean value theorem. Apply the mean value theorem to f on the interval x1, x2. If we do that, what do we get? The mean value theorem tells us that there exists a c on the interval x1, x2 such that f prime of c equals f of x2 minus f of x1 all over x2 minus x1. Again, the mean value theorem says that there is a representative point which this one point alone kind of summarizes the entire behavior of the function on that interval. And what do I know about f prime of c? Candia. What do I know about f prime of c? That it's negative. Since that's negative, that tells me that f of x2 minus f of x1 over x2 minus x1 is negative. And now, basically you're just one step away. Are you guys following this?
Yeah.
This is like a little bit boring, I guess. So what does it tell me?
x2
now I just use just this one last fact, right? That x1 is less than x2, which means that this denominator is positive. And if that denominator is positive, then that numerator must be negative. So f of x2 is less than f of x1. And that was my goal. Okay. Yeah. I'm sorry if that was like a little bit boring. Guys, now suddenly we have so much power. We have a lot of power now. All your whole math lives, you have been given functions, and you've had to just like guess things about when it was increasing and when it was decreasing, and when you had like a relative min and when you had a relative max and stuff like that. Now, with the power of calculus, you can basically figure out anything about anything. Watch. I give you a function. 3x to the fourth minus 4x cubed minus 12x squared plus 5. Please, using calculus, determine and justify when this function is increasing and when it is decreasing. Yo. Hey. We didn't hit the 30-minute mark yet, did we?
No.
Paying attention?
Like 4 minutes.
Okay, cool. Hey, Enoch.
How's it going, man?
It's pretty good. I'm kind of sick.
Oh.
You want to feature
Hey,
the
Libby.
video?
There's a video. We're taping this video right now, and then
Am I part of it
it's
now?
going to be on YouTube. You're kind of
yeah.
not. Your voice is part of it.
You're a new celebrity.
I'm cool with that.
How's college?
Ecology.
Yeah.
Whoa, you're on video.
Hey, no cursing. We're only sophomores. I've heard, and I'm farther away from you than the camera is. So, Libby.
The camera's not very good.
I don't know, Mr. Rose, what is college supposed to be like?
It's supposed to be kind of awesome, I think. Why? What do you think?
I think
It's
I
okay.
worked too hard
It's
for
okay.
having fun.
Libby doesn't know how to have fun.
Trying to get into
Okay, I'm doing a lesson now, so I don't have time to chat.
this. Goodbye.
We get that all the time. I'll see
Okay,
you.
yeah. See ya. You can come back next period. It's like all seniors, a little more chill.
Sounds good.
Yeah, okay. Bye. That was a bunch of college kids. Trust me, they're deeply inspired and excited about learning. They were just trying to act cool for you guys. All right. Anyway, what do? We have to like take the derivatives. So let's do that. And now I have the derivative. I would like to know when it is positive and when it is negative. So I can probably like factor this or something, right? Did you guys do this already?
Yeah.
Okay. I don't want to like get ahead of you. And I think it like works out nicely and everything, right? Oh, look at this beautiful happy function. Oh, yes. Okay, so now that I have simplified the derivative very nicely, I would like to analyze the derivative to see when it is positive and when it is negative. So, okay, this is important. I insist on a particular technique here, which is really helpful, which is, it's not that exciting. You just make a number line, just like we did in pre-calc C, but label your number line f prime, and just like kind of do the thing, right? So, first of all, did I do this right? Yeah. Yeah. So there is changes sign at -1, and at 0, and at 2, and then this is like you guys remember all this crap, right? This is like a cubic, leading coefficient, positive, so the end behavior is like this, so it's like negative, positive, negative, positive. Okay. Thus, I conclude information about the function from information about the derivative. We can make ourselves a little parallel number line for f, and since the function is decreasing on the interval from negative infinity, or no, since the derivative is negative on the interval from negative infinity to negative 1, that means that the function is decreasing, and then increasing, and then decreasing, and then increasing. Cool? Alright, John Park, let's do another one. This one's a little bit harder. Let this function be cosine squared x plus sine x on the interval from 0 to 2 pi. Yeah. Tell me precisely when that function is increasing and when it is decreasing. Professor, you paying attention? Do we hit the 30-minute mark?
We just went over, but still recording.
Oh. That must mean I have a new fancy camera.
Guess so.
I don't need that stupid cat camera. I got my own camera now. Doesn't even cut off at the 30-minute mark.
That wants so much money, but we're getting new cameras.
What?
We want so much money in the C-SPAN contest.
The cap people will come to you now.
Yeah, that's right. Yeah, and you know what I'm going to tell them, John Park, right?
We're the monopoly now.
I don't know if that made any sense.
You are the monopoly.
Monopoly is when like you're the only person who can provide a product.
Yeah, but like our product is cameras over 30 minutes.
Yeah, like, that's true. Yeah, good point.
It's not the only one.
My genius, too much.
Alright. Take the derivative of this thing. Okay, taking the derivative takes about 1 second and it's pretty easy. It's the everything else that's hard, right? How do I begin to analyze this thing? Yeah, let's factor. What should we factor?
Cosine of x.
Yeah, let's factor out a negative too while we're at it. I think that's a good idea.
Oh.
So if I factor out a negative cosine x, then I'm left with like, what is that?
2 sine x minus 1.
2 sine x minus 1. Serious people check to make sure they have factored correctly. Yup, looking good. Alright, so this is my derivative. Now I have to figure out when that trigonometric expression is positive and when it's negative. Okay, so this is something that we did in pre-calc C for like 5 seconds. Do you remember this? Circles? Yeah.
No.
So here's the technique. The technique is you independently analyze when each of the factors is positive and you make a little picture. So when is cosine x positive, for example? Yes. Cosine x is positive all of these places. And when is 2 sine x minus 1?
Wait.
What happened? Oh man! I just blindly listened to Timothy without thinking about what he was actually saying. It's wrong. Timothy, but that does show how much trust I have in you.
Thanks.
Or used to have in you.
Caught on camera.
Okay, cosine is the x coordinate, so it is positive here.